Hey everyone, and welcome. So if you've ever found yourself totally bogged down by those gnarly line integrals in multivariable calculus, you are in exactly the right place. Today, we're going to unlock a massive shortcut, the fundamental theorem for line integrals. And trust me, it's an absolute game changer. So let's just dive right in. So here's our plan. First, we're going to start with a shortcut you probably already know and love from CalcI. Then, we'll give it a serious upgrade for vector fields. After that, we'll get into the key idea of path independence, see the theorem work its magic with a few examples, and then we'll talk about the one all-important catch that you've got to watch out for. Okay, let's get into it. To really get a handle on this new theorem, we're going to build on something you've actually already mastered. We're starting on familiar ground. Remember this absolute beauty from single variable calculus? Of course you do. It's the fundamental theorem of calculus, and it gives us this incredible shortcut, right? Instead of doing a whole Riemann sum, you just find the antiderivative. We'll call it big F, and then just plug in the endpoints, B and A. It's so clean and so powerful. Now, here's the really magical part. The part you might have not thought too much about back then. The answer only cares about where you start and where you end. The whole journey from A to B doesn't even factor in. Now hang on to that idea because it's pretty much the key to everything we're about to do. All right, you ready? Let's take that core idea and see how it gets supercharged for the world of vector fields and line integrals. It's time for the Calc 3 upgrade. And boom, you can see the connection right here. On the left, our old friend from Calc I, and on the right, its bigger, badder cousin for line integrals. I mean, look at the parallel. You're integrating something that acts like a derivative, in this case the gradient, and the result is just the original function evaluated at the endpoints. This little f, the potential function, is doing the exact same job that the antiderivative, big F, did before. It's the same idea, just, in more dimensions. But here's the thing, and this is a big one. You can't just use this shortcut on any old vector field. Nope. It only works if a very special condition is met. And it's that condition that unlocks this amazing property called path independence. So, what is this crucial condition? Well, the theorem only works if our vector field F is a gradient field. You'll also hear it called a conservative field. Don't worry, they mean the exact same thing. It just means that our vector field F is the gradient of some other scalar function, little f. And that little f is our secret weapon. It's called the potential function. And here's the payoff. This is what it's all about. If you can show that a vector field is a gradient field, then any line integral you take through it depends only on where you start and where you end. That's it. You could take a straight line, a crazy looping spiral, a zigzagged path. It literally does not matter. The answer will be the same every single time. All right, theory is great and all, but let's see just how much of a beast this tool is in practice. This is where you're going to really see how much time and headache this thing can save you. Okay, check out our first problem. We need to find the work done by this vector field F, moving from the origin all the way to the point 3, 4. Now, the old way would be a pain. You'd have to parameterize a path, maybe a straight line, plug it all in, and then grind through a potentially messy integral. But we have a much better way. So step 1, we gotta find that potential function f. We're looking for some function where its partial derivative with respect to x is 2x, and its partial with respect to y is 2y. Well, just by looking at it, we can pretty much see that f of x comma y equals x squared plus y squared works perfectly. Awesome! Now we can just apply the theorem. We just evaluate our potential function at the endpoint, f of 3, 4, and subtract what we get at the start point, f of 0, 0. So that's 3 squared plus 4 squared minus 0, which gives us 9 plus 16 for a grand total of 25. And just like that, we are done. No parameterization, no complicated integral, nothing. How cool is that? And it's just a slick in 3 dimensions. For a field like this, if we can see that the potential function is f of xyz equals xyz, we just plug and chug. We evaluate f at our endpoint, 1, 2, 3, and subtract f at our start point, the origin. So that's just 1 times 2 times 3 minus a big fat 0, and we get 6. Simple, fast, elegant. This all seems a little too good to be true, doesn't it? I mean, a shortcut that lets us skip all the hard work? Can we really just use this amazing trick every single time? Well, that question leads us right into our final and maybe most important section. Knowing when you can't use this theorem is every bit as important as knowing when you can. This is how you're going to avoid all the common traps. Okay, let's take a look at this new vector field, f equals minus y, comma x. Looks innocent enough, right? But is it conservative? Is there a potential function hiding in there somewhere? Let's find out. So there's a really quick way to check for this, sometimes called the component test. For a 2D field, let's call the components P and Q. We just need to check if the partial of P with respect to y equals the partial of Q with respect to x. So here, P is negative y. Its partial derivative with respect to y is -1. And Q is x, so its partial with respect to x is, well, it's 1. And there it is. -1 most definitely does not equal +1. What does that mean? It means this field is not conservative. There is no potential function. And that means, and this is the big takeaway, you cannot use the fundamental theorem shortcut here. You'd have to go back and solve this one the old-fashioned way. So to wrap this all up, this is the huge idea we've been building towards the whole time: path independence. It's this almost magical property where the journey doesn't matter, only the beginning and the end. And it's the beautiful gift you get every single time you're working with a conservative or gradient vector field. And that leaves us with a really cool final thought that connects all this math back to the real world. You know, gravity is a conservative force. That's why your change in potential energy is the same whether you take the stairs or an elevator of a building. But what about a force like friction? Think about it. Which forces in our universe depend on the path you take, and which ones only care about where you start and finish? Thanks for watching.